Ladies and gentlemen, dear colleagues, welcome. My name is Deněk Hanzálek, and you are watching the 58th talk of the scheduling seminar. Today, I am happy to introduce Ozcan. He is a professor of computer science and operational research with the Computational Optimization and Learning Lab at the University of Nottingham. He received his PhD at Syracuse University, USA in 1998, some time ago already, and he was supervised by Chilkuri Mohan. Then he worked in Istanbul University at Turkey, and now he is director of Faculty of Science Doctoral Training Center in Artificial Intelligence in Nottingham University. He is interested in scheduling and more widely in computational optimization for intelligent decision support, underpinned by hyper-heuristics, meta-heuristics that are combined with data science and machine learning. And he also likes to tackle challenging real-world problems by these methods. Apart of that, he likes tennis and likes hiking. Ender, it is great to have you here. We are very much looking forward for your talk, and the floor is yours.
Many thanks for the introduction, and many thanks for inviting me to give a talk in here. I have been also following your channel. It's all brilliant. And generally, most of the speakers start with, this talk is related to type of thing, but I think this talk is related to many of the previous talks. And I'm going to provide some references, so probably I'll utter all those names as I go along. Today I'm going to talk about selection hyperheuristics, providing some description of the methods, and talk about origins, motivation, classification. So why are we doing research on hyperheuristics? And then I'll focus on selection hyperheuristics that control perturbative heuristics. And I'm going to introduce a framework, a software, an API and software called HyFlex for cross-domain heuristics. And then HyFlex was used in a competition called cross-domain heuristic search competition. And I'm going to introduce that competition. And I'm going to focus on two specific selection hyperheuristics that are called AdapHH and multistage hyperheuristic, MS-HH. And then I'll start actually, you can imagine that will be the second half of my talk, describing what we mean by automated design or generation of selection hyperheuristics and the current studies or recent studies in the area. I'm going to make an introduction. And I'll move into a framework that we have developed in our research group on apprenticeship learning. And we applied it to open vehicle routing problems. So I'm going to show you some results. And apprenticeship learning involves expert approaches. That's one of the reasons I'm going to introduce AdapHH and MS-HH selection hyperheuristics, because we use them to collect data, and then we try to improve their performances using machine learning algorithms. So the apprentice would be in here time delay neural networks, which I'm going to make again brief introduction. Then I'll have my concluding remarks. I'll try to keep actually all the discussions at a high level so that everyone can understand actually what's happening in here. So I'll start with first state of the art in metaheuristic optimization. So what is the state of the art designing a metaheuristic optimization method? In general, when you look at it, it is really a trial and error process. So what we do is first we start assuming that we have the problem domain expertise, we design and implement algorithmic components which are appropriate for that problem domain. And then what we do is we configure the algorithm and tune the parameters on some selected problem instances. So for example, let's say that we are going to deal with flowchart scheduling, then we come up with a, for example, representation, and then operators to somehow manipulate that representation so that we can conduct a search over the space of solutions, right? So we could come up with multiple operators, and each operator that we come up with could have some sort of parameters. That's why we need that second step, configuring the algorithm, and then tuning those parameters, because now it's pretty clear that parameter tuning helps to improve the performance of metaheuristics or heuristic optimization methods. So generally, we determine a subset of test instances, and as we configure the algorithm and tune their parameters, we actually make use of those selected instances. And if necessary, we revisit our design options and improve the performance of our algorithm. And generally, this is a very time-consuming process, as you can imagine, because it is a trial and error process. And once done, of course, when we think that actually we have a tuned algorithm which performs well in that problem domain, then what we do is we conduct, again, further performance analysis and apply our algorithm on unseen instances from that domain, right? And as a result, we might again have to revisit the design option. So generally, for example, this takes most of the time when you look at the PhDs, taking 3 to 4 years. That's actually how all these colleagues and students spend their time. However, let's assume that we develop, and since everybody knows this metaheuristic, I'll just say genetic algorithm, right? So let's assume that we developed a genetic algorithm for solving the flow shop scheduling problem. Unfortunately, we cannot apply that algorithm if now we have to deal with other problems like recruiting or nurse busting. So you have to redesign some of those components and then go through all this trial and error process once again. It's really time-consuming, right? And that's when hyperheuristics have emerged, because they emerge as a search method or a learning mechanism for selecting or generating heuristics to solve such computational difficult problems. Hyperheuristics represent a class of methodologies for cross-domain search, meaning that once we implement a hyperheuristic that really emphasizes the usability of components, then those search methods, hyperheuristics with those reusable components, can be used for solving multiple problems from different domains. And preferably, those methods should not require any human intervention. So that's the whole idea. So generally, I receive this question, then what is the difference between a metaheuristic and hyperheuristic? Not much. So when you look at the standard heuristics or metaheuristics, they operate on potential solutions directly, right? And hyperheuristics, you can imagine, there is a level of indirectness. So hyperheuristics operates on low-level heuristics. In other words, hyperheuristic algorithms, they conduct search over the space of low-level heuristics, and low-level heuristics at the same time operate on potential solutions. And metaheuristics can be used as a hyperheuristic or as low-level heuristics. But the motivation behind hyperheuristic research is to raise the level of generality of heuristic search methods. What are the limits? Well, when we look at the literature, we can always see this, right? So, for example, for flow shop scheduling, let's say problem A represents that. For flow shop scheduling, we have specific solvers which are very successful in solving such problems. But for B, for example, represents another domain, let's say nurse busting, and C represents, let's say, recruiting. And for each one of these problem domains, we have specific problem-specific solvers which are working really well. They might not be actually, we always have a best algorithm for solving such problems, right, in general. So the question is, can we somehow come up with a general solver which can be applied to all these problem domains? So I think, just as an example, I think on recruiting domain, is the paper from David Pessinger and Stephen Ropke in Computers and Operations Research. And in their paper, I think it was in 2007, So they provided one single approach to solve 5 different wake routing problems, from wake routing problem with time windows to open wake routing problem, right? So it means for in ABC, instead of totally different problem domains, now with that paper, we were able to solve, using just one approach, multiple wake routing problems. So that represents some sort of a level of generality, but can we make it even more general so that we can solve fundamentally different problems using the same approach? Or at least, how can we create reusable components so that we can at least do not change particular parts of the algorithm, but solve problems from multiple and different problem domains. So of course, we know that the general solver doesn't exist yet. However, if we consider the gap in between the current state of the art and the general solver, there is significant scope for future use in the hyperheuristic area. Of course, hyperheuristics, you can consider them to be adaptive methods in search and optimization. So there are many other well-established related areas. So for example, adaptive operator selection or algorithm configuration, algorithm selection and portfolios, co-evolutionary frameworks, multi-mimetic algorithms, for example, or mimetic computing, hybrid metaheuristics, meta-learning, parameter control, reactive search, variable neighborhood search, and even more, right? So now I'm going to move into the classification of hyperheuristics. This is really not far away from existing knowledge, I should say. So depending on the nature of the feedback a hyperheuristic method receives, either a hyperheuristic can embed an online learning mechanism, or we can consider that hyperheuristic to be an online learning hyperheuristic, or if the hyperheuristic is operating in a train and test manner, then we can call such hyperheuristics offline learning hyperheuristics. So the feedback mechanism actually requires hyperheuristic to be trained on a given set of problem instances, and then whatever is learned is used to solve other unseen problem instances. Or hyperheuristic might not have any learning mechanism at all. That's also a possibility. And when we look at the low-level heuristics that hyperheuristics control, there are different types of approaches. So what we call, there are selection hyperheuristics and generation hyperheuristics. The selection hyperheuristics they generally use fixed heuristics, which are mostly designed by humans, and those heuristics can be constructive or perturbative. Perturbative heuristics meaning that all these heuristics accept complete solutions and can process complete solutions and output another complete solution. Constructive heuristics can process incomplete solutions, and generally they build towards a complete solution. That's the distinction. And the heuristic generation methods also can generate constructive or perturbative heuristics, and generally these are automatically generated from the components provided by humans. So they have a different nature. And in general, for example, genetic programming is used as a generation hyperheuristic. And I provided in here a paper from Frank et al. On automated design of production scheduling heuristics. It's a review paper, and when you look at it, it somewhat shows that actually in the scheduling community, this is one of the topics, one of the hot topics in the area, to design such approaches automatically using genetic programming. So coming back to hyperheuristics in general, everything I would say started with these papers in 1960s. So Fisher and Thompson, they tested different learning mechanisms for mixing two heuristic rules at the time for job shop scheduling on some small instances. So those actually had some number of jobs, and they need to be processed using some sort of operations, and they were really small at the time. So, for example, number of jobs, I think it was about 6. It varied just from 6 to 20, and the number of operations they just varied from again it was either 5 or 6. So it was really few. And when they actually applied their approaches, their conclusion was interesting because they thought that actually learning is possible. However, when they look at the performance of the approaches, mixing rules, heuristics, they perform better than each heuristic used on its own. And they just hypothesize that actually in the future, you can there will be much more complicated problems, and there will be other heuristics or rules developed in the area, so which will allow users to combine their strengths and then get better performance, better than the performance that they actually received on these small problem instances. So then in 1975, this important paper came about, the algorithm selection from John Rice. This is kind of one of the interesting, let's say, papers in the area, because John Rice was suggesting that we can learn from problem instance features and map them to the best solver. In other words, instead of we make use of existing solvers, we test their performances, and then for each problem instance, we associate them with their features, and then we have a mapping from that feature set to the best performing algorithm. So which means that if you have an unseen problem instance, we can use their features, and we can directly find out which algorithm we need to apply to solve it more effectively. So that was really an interesting paper in the area. So then in 1990s, and what we had was, again, in job shop scheduling, colleagues have applied different type of approaches. They evolved rules to solve different, let's say, job shop scheduling problems. And then in 1997, this is the first paper where the hyper-heuristic word that appeared. And they were just trying to combine different types of AI methods for ATP systems. And I would say one of the influential papers in the area has been the Calvin paper. And they basically suggested they described most of the simple hyperheuristics at the time in that paper. And they proposed this type of a framework. Right? So they introduced, Calvin et al., this paper introduced the concept of domain barrier. Unfortunately, that led to initial limited hyperheuristic interface, which I'll be discussing in a bit. In this framework, the hyperheuristic simply chooses from neighborhood nodes, which are called domain-level heuristics or low-level heuristics. And in return, it learns about the current solutions based on the objective value. So it just, the problem domain barrier does not allow any information to flow through towards the low-level heuristics, or which is called problem domain layer. However, the hyperheuristic can maintain some data structures, internal data structures, and statistics about the performance of low-level heuristics. Right. Yep, that's it. So this, unfortunately, as I said, introduced a very limited, narrow interface, which was followed with, let's say, all of the following papers. So this one shows the recent applications of selection hyperheuristics, and when you look at them, you can notice that actually one of the most popular areas is still scheduling and vehicle routing. So the hyperheuristic framework suggested by Calvin et al. Consists of perturbative low-level heuristics, and these are all fixed. We know ahead of time what those heuristics are. However, the hyperheuristic layer has no information whatsoever. It just knows that there are n low-level heuristics, and it has to choose one of those heuristics to apply to a solution in hand, and then creating a new solution, and then decide whether to accept or reject that solution using a new acceptance criteria. So in other words, this type of single point based search hyperheuristics, they have two key components: heuristic selection method and new acceptance method. And they have this, generic and very standard stochastic local search framework. So they choose from a subset of heuristics, apply it to the current solution, and then decide whether to accept or reject a new solution. That's it. It's really a very simple framework. And when we look at the heuristic selection methods, these are kind of the initial ones, which shows actually we have many out there. There are, heuristic selection methods with no learning. So we could use, for example, simple random or random permutation. Then generally these are combined with learning new acceptance methods. So there's still some sort of learning aspect to hyperheuristic research. And heuristic selection with learning, we have, again, as you can see, many different components. I'm just showing this slide simply because to point out reinforcement learning and its variants. There are many variants of it, and I would say choice function is one of them. It has been in the scientific literature for a while now, and they have been used as part of hyperheuristic designs. So we have this extended classification of hyperheuristics. This extension is really just for your information type of thing, because when you look at it, we have a paper where we classified new acceptance methods. They can be stochastic or non-stochastic. Non-stochastic new acceptance methods can be split into basic and threshold. And all the move acceptance methods, they have some sort of a parameter setting, either static, dynamic, or adaptive. However, these all the concepts also apply to the parameter settings, especially heuristic selection methods as well. So you can find all the details in these papers if you are wondering how actually selection hyperheuristics are used. Just to show you, that with this classification, you can find a paper which falls into those categories, interestingly. I'm really not going to go into the details of it, but, this is just to show that actually there is even more information on selection hyperheuristics in those papers, which you can refer to. So coming back to the Calvin et al., the suggested framework, as you can see, this hyperheuristic flexible interface is designed based on that framework. So it was at the time designed for researchers to prototype their hyperheuristic designs quickly on different types of problem domains, and also to create a standard API. So this was implemented in Java at the time, and its location has been changed. So I included its location in here, where you can download the HyperHeuristic implementation in Java from this website. So in here, what happens is, we just go this. So again, we have the hyperheuristic layer and we have the domain layer, and this HyperHeuristic respects the domain barrier, meaning that in here, hyperheuristic, for example, has only the informational memory locations. So for example, from 1 to n, but it has no knowledge on how, for example, a solution is implemented. So what this system can do is, the system knows also how many low-level heuristics exist, n of them. So it can just say, use the if operator, apply it to the solution in the jet location, and then save the new solution in the ket location. right? So that's actually the message that it can pass to the domain layer. So this layer has no information whatsoever about the problem domain specific information. And in here, the domain also, Hyper-heuristic layer can ask, what is the objective value of the new solution in location K? So that's it, and nothing else, no other information is allowed to pass through this domain barrier. And then Hyperheuristic was designed at the time, as I said, for rapid prototyping of different Hyperheuristic selection, Hyperheuristics designs. And colleagues at the time used that interface, used the implementation of the interface, Hyperheuristic, for a competition. And as they get prepared for the competition, they implemented 6 different problem domains, including, maximum satisfiability, bin packing, flow shop scheduling, personnel scheduling, traveling salesman problem, and vehicle routing problem. And in here, what you see is all the heuristics, they have certain IDs. So if you pick a problem domain, let's say, for example, vehicle routing, if you look at it, it has, since we start counting from 0, there are 10 low-level heuristics. They are all implemented for that domain. And the AdapHH1, this means low-level heuristic 0 with that ID. It's a mutation heuristic. Low-level heuristic 1, and low-level heuristic 1 is mutation, second mutation heuristic. And low-level heuristic 7 is the third mutation heuristic. So there are 3 mutation heuristics. And there are 2 mean and recreate heuristics. And there are 3 hill climbing heuristics or local search heuristics implemented within the framework. So all the problem domain level or the layer, let's say, components for the algorithms are already implemented. It's that. So this leaves the implementers, or let's say users, just to implement the hyperheuristic itself. So hyperheuristics provide this, separation between the control and all problem domain level details, and this framework and then this interface implemented the domain barrier and that concept. So what happened was TSP and VRP, traveling salesman and recruiting problems, they were not disclosed to competitors. There were 10 training. Oh, can you hear me?
Yes, we can hear you.
Okay, for some reason it shows, microphone has been changed, but okay, that's fine. So there are 10 probably public training instances for each domain and 5 test instances. The public training instances were disclosed to all the competitors. There was a set time limit, 10 minutes. We can call it 10 nominal minutes, because that corresponds, they did some benchmarking on competition machines, and they come up with also, they provided that benchmarking tool. If your machine is slower or faster, you can use that benchmarking tool and see what 10 minutes corresponds on your machine in that respect. But that was the idea. So each hyperheuristic in the competition given the same amount of time, and they are run for 31 trials. And the median results were used to rank each competing algorithm. And the first ranking algorithm, they were given a score of 10, second 8, and so on. This is Formula One scoring system. So that system was used in scoring and deciding the winner of the competition. Right, so the winner turned out to be Katja Verbeek, Patrick de Kozumaker, and Griet van den Berg. They entered into the competition with their student, Mustafa Mısır, and Mustafa Mısır's algorithm turned out to be the winner, which is called GIHH or AdapHH. and the score of the algorithm was 181. Just going back to the computation, so these were tested on 6 problem domains, and for each one, 5 test instances, unseen instances, well, 5 test instances were used. For the public domain, 3 training instances and 2 hidden instances were used. So in total, 5 times 6, we have 30 problem instances, and with the Formula 1 ranking score, the maximum score could have been 300. So if you look at these results, AdapHH performed extremely well. Its cross-domain performance was brilliant. And when you look at the algorithm, which is close to AdapHH, it just scored 134. So this was a really, really very successful and elaborate algorithm at the time. When you look at the components of AdapHH, it is really very nice and elaborate components. So it's, first of all, it's a multi-phase approach or multi-stage approach, which, for example, it is a mechanism for heuristic selection, adaptively deciding on the subset of low-level heuristics to use at each phase throughout its duration. And they called the selection method, I think, adaptive heuristic set, AdHS. And the performance metrics for each of low-level heuristics were maintained as expected. And the system excludes poorly performing low-level heuristics, and also even sometimes excludes it fully from the whole set. Also, AdapHH used an interesting approach. So the approach was, why to apply just a single heuristic, right? So let's actually combine pairs of heuristics to create new heuristics. So it just maintained the list, and this is called relay hybridization. So they employed relay hybridization and maintained such a list, and also a probability vector of choosing a low-level heuristic. So based on those probabilities and using automatons, they have chosen the best appropriate low-level heuristic at each step adaptively. So this was a really brilliant approach. However, this approach, although great, introduced over 30 parameters, and the colleagues tuned those parameters and obtained this brilliant performance out of the approach. So I just wanted to also introduce here just this paper, which actually refactored AdapHH, the code of it, and using accidental complexity analysis. And they also provide the lean GIHH, which is actually a variant of AdapHH, which improved the internal structure without changing its functionality. And you can download and start using them either way. So that's the first hyperheuristic I wanted to introduce. Now this is the second one I would like to introduce, iterated multistage selection hyperheuristic. So within, let's say, after 5 years of AdapHH being introduced, there was no other selection hyperheuristic outperforming AdapHH. So this one is the one which, let's say, not outperformed, but performed better than AdapHH. That's why I'm introducing it. And there's a second reason, of course, and I'll come to that in shortly. So in our approach, we ignored crossover operators because that requires maintaining second solutions, which will be provided as arguments into the crossover operators. So we just exploited only a single point-based search framework. So we had parameter settings, intensity of mutation, which is applied to all mutational operators, including ruin and recreate. And depth of search parameter was already provided as a part of HyFlex, which influences the behavior of all hill climbing operators. So we discretize them. Instead of using a real value between 0 and 1, we discretize them. And we have chosen a random value, and the same value is as long as there's improvement. Otherwise, it is set to another value randomly. So this is the framework we have. We combine two hyperheuristics together in different stages. And the transition from one stage to another, generally, it relies on a probability. So we had a parameter. So in, for example, stage 1, what happens is we assume that we have a subset of low-level heuristics, and each heuristic within that subset has a score, right? And we use somewhat softmax strategy to choose the heuristic in this stage. And then we applied the chosen heuristic, and we used an adaptive threshold move acceptance method in this stage. So stage 1 terminates after a certain duration if there is no improvement. Okay? So when we look at the adaptive threshold move acceptance method, I'm not going to go into the details, but all I'll say is it is based on, it's a function of the best found solution so far in a given stage, and also an integer value in a circular list. So what happens in here, as you can see, this shows behavior of the adaptive threshold move acceptance. It is just a very simple logic. So that is, if we cannot make any improvements in a given stage, we just allow actually change the level of threshold so that allow worsening solutions. And still, if we cannot make any improvement, we change the threshold so that even more, let's say, the cost actually increases so that we allow worsening solutions with higher cost in that regard. And this just shows a minimization problem. And in the long run, hoping that actually there is improvement in the cost. So stage 2 hyperheuristic is important because in stage 1, we have a certain subset of low-level heuristics, and each low-level heuristic has a certain score, which does not change. But how do we decide on the scores, and how do we decide on the subset of low-level heuristics to be used in stage 1? So that is actually decided in stage 2 hyperheuristic. In stage 2, we apply a very generic hyperheuristic that is greedy. So we use all the low-level heuristics and apply it to a solution, and then accept the one which makes the most improvement at each step. However, we modified this logic, and we apply, first, we use the same idea, well, similar idea, not the same, as AdapHH uses. If we have n low-level heuristics, we paired them up and created more low-level heuristics. So making n plus n squared. And here we have an example. If we have 2 low-level heuristics, then we can just combine them and create actually more low-level heuristics, like in total ending up with 6, that is n plus n squared. So what we do is now we apply all the low-level heuristics to a given, we can apply all these low-level heuristics. However, we want to reduce it. We increase it because hoping that this relay hybridization will help actually to improve the performance of the overall performance of the selection hyperheuristic. So we reduce the number of low-level heuristics now and assign a probability to each one. So how can we do that? So we use, again, a simple logic. In multi-objective optimization, if we know Pareto optimality, we use that concept. In other words, what we said is, now imagine at each stage in here, at each duration until S2, a final duration, we have tau seconds to use. So we apply all the low-level heuristics to a given solution, and then at each stage, end of the stage, we decide we can find out actually which one is the best, which solution has the best objective value, and which low-level heuristics achieved actually that solution. So in other words, we start with this one, and we apply all these 6 low-level heuristics, and this is the best at this end of the stage, best solution found so far, and this solution is achieved by low-level heuristic 1 and low-level heuristic 2, right? So we use that best solution for the next stage, and we apply all the low-level heuristics, and again decide which low-level heuristic has the lowest objective value, right? And so on. And in all these stages, we all know the best ones. However, the logic is in here like this. So we want to find out which low-level heuristics using short period of time makes the largest improvement. That heuristic is equivalent to us if a heuristic actually in the long run makes improvements, right? So that's why we use that Pareto approach in here, Pareto optimality concept, and we use the ones on the Pareto front, all these solutions, and we consider only those low-level heuristics which actually created these Pareto front solutions. So in here we have low-level heuristic 1, in 3, 1, 2. So in total we have 4, now in total 3 different heuristics. So from 6 now we reduce the low-level heuristics into 3, and the count actually forms the probability of each, or the score for each of the low-level heuristics. So then we pass this information from this stage into stage 1, and stage 1 starts its operation. So our algorithm has 6 parameters, and those 6 parameters were tuned, and these are somewhat the results that we have obtained. And when you look at the results, you'll see that interesting things have emerged. So for example, in here, when you look at the personal flow shop scheduling domain, the system automatically finds that it should apply a mutation operator and then a hill climbing operator. This is somewhat imitates, let's say, if you consider just as a step, it imitates the behavior of iterated local search or memetic algorithm. This is really interesting. So the system automatically adapted to find this. And as you can see, not in all the domains that, you know, relay hybridization is working. So for example, in personnel scheduling, relay hybridization did not work, right? And also recruiting problem, right? So when we look at the performance, compare the performance of the multistage HH and MS-HH with each hyperheuristic from each stage, MS-HH performs significantly better than in almost all instances, not all of them, but let's say majority of the problem instances, it outperforms S1HH and S2HH. And when we compare it to the competing algorithms in CHESS 2011, it just scores 163.60, performing better than AdapHH. Right, so now I'm moving into automated design of selection hyperheuristics. There are many different methods that are being used. So I have given some examples in here in this slide. So it's not just genetic programming, but there's also grammatical evolution. And in a way, you can assume algorithm configuration is part of this. So Adriansen, for example, et al., they perform meta-level search using ILS to configure actually a selection hyperheuristic. And there are also other papers which shows how you can make use of Monte Carlo tree search, gene expression programming, conditional Markov chain search, and so on. So the last one here shows reinforcement learning. Again, it is really to choose components of ILS. In general, gene expression programming, grammatical evolution, or genetic programming, they are used to generate automatically selection hyperheuristics to solve various problems. And what we are proposing in the study that I'm going to introduce you shortly, use of apprenticeship learning. So learning by demonstration. So just to illustrate this concept, and these are the relevant papers, by the way, when you look at this robotic, generally this is a concept used in robotics, by the way. So there's a human expert. The human expert shows robot to how to achieve certain tasks, right? So there was a robotic arm also, which I have seen actually. There are videos, for example, controlling a car or a helicopter, or for example, a robotic arm to pick up an object and move it to a target destination type of thing. So a human shows the robot how to achieve those tasks, and robot using in the background machine learning algorithms understands how to accomplish unseen tasks, but similar tasks, of course. So working with a colleague in the area of robotics, so we imposed the question, can we automatically design a new selection hyperheuristic by observing an expert hyperheuristic in operation? So is it possible? So that's why we came up with, just to see whether we can do this. But please do not forget this. If we already designed the approach for solving a problem, if we cannot exceed its performance, then there is no point in designing a new algorithm, right? So this is when I say, learning from a selection hyperheuristic, of course, our goal is somehow to exceed the performance of that approach, hoping that data science or machine learning discovers hidden patterns, constructing effective algorithmic components. So in here, for example, just as a reminder, what we have is this selection hyperheuristic framework, single point based search framework, right? And in this framework, you can consider any problem domain. I just, focused on VRP because we applied the framework that I'm going to describe to open VRP problem using HyFlex framework. We use the same low-level heuristics provided by the HyFlex framework. So in here, heuristic selection decision, when you consider it, we have n discrete choices. So for example, for VRP, we have from 0 to 9, 10 different options. And for move acceptance, it's accept or reject, right? So if it is improving, we usually accept it, right? If most of the move acceptance decisions are like that. So, and in selection hyperheuristics, I haven't seen any actually such approaches where an improving solution is rejected. So that's why we decided actually within our framework just to focus on if the, let's say, new solution is equal to the objective value is equal to the input solution, incumbent solution, or if it is worsening, right? Those cases are very important, whether it's accepted or not, right? We want to somehow find out the ones, equal moves or worsening moves, or in other words, non-improving moves are accepted or not. So that's our focus, and that's also a classification task, right? So hence this framework. So we have a certain problem domain we want to apply, and this apprenticeship learning framework is based on train and test framework. In the training stage, we have identified two phases. First of all, we need to collect features. This is the data collection part. And those features plus we need actions. So those actions are, for example, heuristic selection and move acceptance outcomes from the expert hyperheuristics. So we run the hyperheuristics, expert hyperheuristics or hyperheuristic, and we collect this data from that hyperheuristic. And then we construct the data set, right, on some pre-selected sample instances. This is for the training phase, right? Then we train it using some machine learning algorithm to generate classifiers for heuristic selection and move acceptance. And once we have those classifiers, we put them together, we combine them, forming a new hyperheuristic. right? Now it's testing time. So in the third phase, we apply the generated hyperheuristic to unseen instances. So this is the framework we proposed. So we have chosen the open vehicle routing problem. So in open vehicle routing problem, in that variant, vehicles are not required to return to the depot at the end of a route. So a route ends after servicing the last customer. And we use the same low-level heuristics as provided in high-flex domain. So for example, low-level heuristic 0, that's a mutation operator which swaps randomly selected two adjacent customers within a route. AdapHH is a ruin and recreate operator along with AdapHH 3, and AdapHH 2 selects a number of customers to remove from the solution based on their proximity to a given location. And as an example of a hill climbing method, AdapHH 4 accepts the first improvement, repeatedly swapping the current city and the next nearest city to it, right? Right, so that's our problem domain. I think I'm going to describe also the in our approach, we use a few different. So first of all, let me put it this way. So in here, I'm providing a reference to a paper. So I'm going to talk about a recent study that we have conducted, but actually all these studies started in 2016. So it's not somewhat new in that sense. Until we get to this point, we had to do a lot of experiments. So as a result of all these initial studies, I'll consider that initial study. Even the study that I'm going to discuss in a bit, I consider it to be initial. So we tried out different machine learning algorithms to create classifiers. So we tried out multi-layer perceptrons, C4.5 decision trees, and a time delay neural network. And time delay neural network performed, I would say, slightly better than the others. And what we noticed was hyperparameter tuning. Parameter tuning is still important in machine learning, and number of neurons in the hidden layer turned out to be the most influential factor on the hyperheuristic performance in the time delay neural networks. So we used Taguchi design of experiments methods to tune the number of hidden nodes, learning rate, and momentum, all these parameters for the time delay neural network. And we find out that 24 is the best for the hidden nodes, 0.07 is good as learning rate, and 0.9 for the momentum. Right. So in our initial experiments, we used a variant of choice function, but we ignored the move acceptance just to simplify things, just to see whether there is any value to the approach, and the results confirm that there is. And also we tested two versions of the approach. That is, we collected, for example, information. Just remember, we are using HyFlex-based framework for the OpenVRP, which is extremely narrow interface. So we cannot ask any information from the problem domain layer that the interface does not allow. So the only thing we can receive is objective value, right? So we used, let's say, as a logic, we used the distance between objectives. And we used a number of steps. We maintained that as a feature, and then what the heuristic is selected, so that actually we can collect all that data. And the second version, we have broken the HyFlex interface. We did not use just one bit of information, that's the distance between objective values between incumbent solution and the new solution. We also used their distances, representational distances, like Hamming distance, right? And then we have, again, observed that more information helps to improve the performance. So in the in our next stage of experiments, so what we did is, why are we using just one expert to collect the data? Why don't we use multiple experts to collect the data? And also, why don't we generate move acceptance methods and combine it? They are also classifiers. Why not combine them together and see what happens? So we use time delay neural network on the collected data, and we run AdapHH and MS-HH, multistage hyper-heuristic, as multiple experts for data collection. And we did that on the OpenVRP problem domain. So when you look at our data collection phase, we just used the objective differences, and for n steps, we collected all the data line by line, right? So objective differences, right? And this is the representational distances between the incumbent solution and the new solution, and for n steps. So those are the features or instances in the machine learning file. And we did the same for move acceptance. We collected each from two of the experts. So expert A was AdapHH, B was MS-HH. We used 8 as for the n value. We tried out several values for n, but this turned out to be the best. So in here, the reason actually we are using, let's say, observing multiple as features, multiple entries for objective value differences and distances in that regard. Because, for example, reinforcement learning is one of the successful heuristic selection methods. It just considers individual performance of low-level heuristics. So it just considers, at each stage, just looks at the score. And there is a choice function which also considers pairwise interaction between low-level heuristics. And we were hoping that there are some hidden patterns between the heuristic value changes and also changes in the distance between different solutions, solution representations. So we decided to go more like that's why we have n equals to a. And we generated also data, right? So using both AdapHH and MS-HH data. Also, we split them. So as an apprenticeship learning, we said, okay, let's only use AdapHH data. And also, we said, okay, let's use only MS-HH data to generate new selection hyperheuristic. So in a way, we have 3 different apprenticeship learning hyperheuristic using the associated data. So we used standard OpenVRP benchmarks from the literature, which are categorized as standard, large, and very large. So first report, so we trained the system, and this is the results for using both experts while learning. So, and in here, what you see is exact match ratio and area under curve, AUC, they are used as performance metrics. Exact match ratio indicates the percentage of samples that have all their labels classified correctly. And OG indicates models' discriminative ability. So the higher, the better for both values, right? So when we look at the results, as you can see, exact match ratio is really incredible for all those values. We have a score between 0.61 for area under curve to up to 0.956. So that demonstrates that classifiers have learned some information about the class. Right. So then we did some further analysis looking into utilization rate of each low-level heuristic. And utilization rate is calculated as the number of improvements that the low-level heuristic yields over the best solution found, and that is divided by the total number of improvements. So we are focusing on improvements only. As expected, local search heuristics, they are actually, they lead to the majority of the improving moves. What is surprising is in OpenVRP, we would have expected that when we create our somewhat smart operators, being smart mutation operators, should perform slightly better than mutation. But in this case, in our cases, mutation actually performed better, making more improvement, creating more improved solutions than as compared to ruin and recreate. And the distribution of all these improvements to each one of the low-level heuristics is provided in here. What you can see in here is, again, if you use both of the data from these experts, the behavior of the low-level heuristics, definitely they are different than what we have for either of the expert systems. So what's the result then? So in here, what we see is the average rank out of 5 methods for each set of instances, with a lower rank indicating better performance. So first of all, apprenticeship learning using data from both experts turned out to be top-ranking approach, right? So this one shows the overall ranking. So we conducted experiments and repeated for 30 trials, by the way, for each instance. So in the overall, taking the average of all the ranks, the apprenticeship learning approach using data from both experts with an average rank of 1.62 ranked the top. And then comes the apprenticeship learning hyperheuristic, which learned how to choose a heuristic and how to apply move acceptance from MS-HH, ranked the second. If you look at this one. And also apprenticeship learning approach using both expert data performs significantly better than all except the MS-HH, apprenticeship learning MS-HH. And I'll just jump to the last one in here. AdapHH somewhat, as you can see in here, ranks the worst with an average rank of 4.5. And when we look at all the instances, AdapHH cannot provide any best performance in any of the approaches. So this is probably because also this shows the effectiveness of the learning strategy in here, because we do it in a offline manner, while AdapHH is an online algorithm where it tries to learn which low-level heuristic to choose and with what parameters and so on. So learning is also costly, and this shows actually effectiveness of applying this technique, which learns in an offline manner. So we did even further experiments. So what we did is we selected some instances from standard subset, and then applied it to the standard itself, the remaining unseen parts, and so on. And then we trained it using the standard instances and applied to large data set, and then to very large data set. And then we trained it on large data set, and then applied it to very large data set, and so on. This just shows the results and counts the number of instances where this algorithm A performs significantly better than algorithm B in the first column in here. And if their performance is similar, that's the third column. And if the performance of the second algorithm is significantly better, it shows on the second column, right? So this highlights the ability of the proposed method that generalizes well. And since statistically significantly better performances observed almost more than half of the instances tested. Of course, this was somewhat expected because we did not do anything. We did not process the data that we collected. That's basically raw data. It just, we compute the difference in the objective value and the distance between two solutions, input solution and output solution. And that's it. That's what we use. And as the data set grows, of course, their objective values and also the distance between two solutions could grow even further than expected. So we were somewhat this was expected. So these are not brilliant results, but they are really good results, very promising. Right, so concluding remarks. So this is actually about HyFlex first. So HyFlex framework has been in use for hyper-heuristic research and benchmarking for more than a decade now. And hyper-heuristics with reusable components are general purpose and effective intelligent search methods. And the number of studies on hyper-heuristics have been increasing incredibly. So HyFlex framework and all other frameworks, they put search methods on a much more experimentally rigorous footing. It's very important. However, we should not ignore the implementation issues. At the end, humans are using the frameworks, and it is possible to break the framework. Although we are expecting fair comparison between different algorithms, but if someone uses wrong features or breaks the framework, they could be running their hyper-heuristic for a long time. So that's why a good practice would be, if you are using HyFlex framework, colleagues should provide their codes. Otherwise, I would be very suspicious of the experimental results. And we have such papers in the community, unfortunately, which we are unsure, as we cannot replicate the experiments. And especially with hyper-heuristics, the technology is kind of advancing. So the latest thing we find out a couple of weeks ago is that if you are using Windows 11, the benchmarking tool also breaks now. So it's very difficult to say, those experiments using Windows 11, whether, a fair environment is used on. Regardless, so still HyFlex framework in a way builds an invaluable communal source that is of benefit to both practitioners and researchers. And in our experiments, we already show that the standard model using hyper-heuristics, like one-off with opaque domain barrier and no learning between instances, can be extended without loss of domain in generality and loss of domain independence. There is still a need for more flexible modular tools with reusable components that support information-rich environments. That need is really growing in time. And my last slide. Now I want to comment on the approach that we developed, apprenticeship learning approach. So machine learning can effectively find hidden patterns in the heuristic selection and move acceptance choices of multiple experts. But I should maybe highlight the word tuned machine learning methods can do that. And we always wondered whether student surpasses the teacher, and in this case, it does. The generated selection hyper-heuristic not only outperforms state-of-the-art methods, but also generalizes quite well, solving the unseen, in our case, open vehicle routing problems instances, even larger than the ones on which the apprentice was trained. Right, so there are still many issues, open questions to be explored. That's why I called even our last study as an initial study. For example, data collection. So for how long should we run the experts? And for how many trials? So in our case, we run one trials, we used multiple instances, and it was 10 nominal minutes, but why not increase it to 20? But if we increase it, then what? So there are a lot of questions there. And as mentioned before, enabling widespread reused and shared knowledge discovery, it is really important that perhaps all these data collected should not go in vain. We should somehow share it. So we need really data repositories for that purpose. So also, we did not do much of feature engineering in here. We just used those features that I described in my presentation. However, we know that there are other possibilities. So for example, we did not apply any normalization. And as the problem sizes increase, as you can imagine, the distance between objectives and the distance between solution representations could vary a lot. And normalization is likely to help in the learning process. And also, there are issues, there might be some issues, especially in the feature engineering part also. I think a good question would be, what features can we use to improve the learning process further? So other than just objective and distance between representation, what other features can we use? And depending on the hyperheuristics used as expert or the problem domain, the imbalanced data could become an issue. So in that case, how can we balance the data? There are, of course, standard techniques like undersampling, oversampling, smooth, and so on. But would they be useful? And also, well, these are all somewhat interrelated, by the way. How can we expand the generalization capability of the machine learning models that we generate? So can we apply the same classifiers that we create using one problem domain to another problem domain? So that's why I'm saying, with this feature engineering is also important, and it relates to generalization, exploration of generalization capability of such approaches as well. Right, so why am I saying, I'm seeing actually a potential there just for a simple reason. For example, we are using the same approach, right? Simulated annealing to solve recruiting or nurse fasting. Why can't we do with this machine learning approach as well? It just requires careful design of different components from my perspective. So the next one is which machine learning method to use for what purpose. So in our case, we did not deal with the parameter, let's say, parameter control issue. So all the low-level heuristics designed underneath HyFlex, they have a parameter setting which can be controlled during the search process. So can we somehow use different approaches? So those parameter values are continuous. So for example, can we use classifiers to create heuristic selection methods, but at the same time use linear regression, for example, to predict which parameter value we should be using at a given time. So mixing different ML approaches. Maybe I should mention one thing in here. Since large language models are extremely popular, there's a paper coming up, I think it's in the archive now, which is talking about a large language model applied to evolutionary algorithms to create metaheuristics automatically. So I think they are creating 1+1 EA type of approach using large language models. So it's interesting. Colleagues, I had a note in here, Nikki Weinstein and Thomas Beck. So that's an interesting paper I would suggest. And there's, as usual, once AI is in the picture, there's the explainability issue. Now, this issue becomes even worse when you consider with machine learning, we are creating a heuristic which are applied to different problem instances. So how can we explain at the first stage what ML captures and how that influences the search behavior of the automatically generated algorithms? Those are all valid questions. And as I have mentioned before, there's plenty of scope for research in this area. Thank you.
Okay, Ender, thank you very much for your very informative talk. And now let me ask the audience if anybody had a question. Anybody should be able to unmute the mic. talk was a bit longer than.
Zdenek, I have a hard time hearing you. Huh? For some reason, you don't come very loud.
Okay.
At least with me.
So please, questions.
Okay.
Mike, do you have any question?
If nobody has a question, let me ask a question. But I see that a lot of people are not unmuted yet. Ander,
Yes.
do you know any one of your ideas, and especially any machine learning ideas, that actually have been applied into a scheduling system in industry? That you know about the actual implementation in industry?
I know colleagues in China, they are working on some sort of port scheduling problems. So they are actually looking into it. And as from my perspective, so what we did is working with a local company in here, we tried to use machine learning for tuning the low-level heuristics that they are using solving recruiting problems.
Recruiting problems, okay, for human resources?
No, it's definitely for their customers. So this is a software company, and they have been using, developing recruiting solutions.
Oh, for vehicle routing problems. Okay.
Yeah. And what we did was we applied, so we left the framework with them. So I'm quite sure they are using, at least for illustration and demonstration purposes, how that approach works to their customers.
Okay, thank you.
Yeah.
Okay. Any other question from the audience? If there is no more questions, it was really quite long. So let me conclude the talk. Thank you, Ender, once more. It was really very nice. And there are vacations coming, so the next talk will be in September. We don't know yet when it will be exactly and who will be the speaker. So I will distribute the announcements, and you can also follow our webpage to see who will talk. But definitely we will continue in our seminars. This spring we had a little bit less speakers, but it was due to, let's say, organizational issues, I think, because some people rejected and some people moved their talk. But I believe that in September we will restart in a full strength. Thank you very much for being with us, and looking forward to meet you in September.
Thank you.
Thank
Okay.
you. Hi, Google.
Thank you. Thank you.
Have a very nice summer.
Thanks.
Bye.
Bye-bye.
Bye.
Bye bye.
Bye-bye.